Hello. So in this video I want to go over a very interesting experiment that I did back in, it's going to be 2014 now, called the Tesla Hairpin Circuit. And I'm going to spend a little bit of time talking about the circuit itself and then go into the phenomenon here. So I'll start by going over to a curious website called Transformicom. And in this website, it's just nice to show a little bit of the overview of the device. This is an image from Tesla's patent here, and it shows the general setup of the circuit here. So you'll have a high voltage transformer. There will be no mid-tap, it'll be end-to-end, and you'll have a spark gap from D to D here, and two AC capacitors wired up in you would say series, because on the other side of the capacitors there will be a stout copper bar, and Transformicom explains basically what Tesla explains in simpler language. And the stout copper bar creates a transmission line where impulses from the capacitors discharging across the spark gap after they've charged from the high voltage transformer creates very high current surges in this section of the circuit. So this is what they would often call the conventional electricity portion of the circuit, and this is the high frequency transmission line portion of the circuit where interesting things happen. And Tesla goes into how it's amazing you can light up a light bulb even when there's a short circuit across it, but anyone that's done high frequency electronics or transmission line electronics or engineering know that there are nodes at quarter wavelengths that you can attach loads across, and you can put things like stubs and shunts across these lines, and often a impulse, if it's properly impedance matched, will light up a load just fine with short circuits. So this is very much a high frequency transmission line, and in his early days Tesla was very fascinated with the high impedance phenomenon, because as you know, with the capacitor there's a high impedance when you put 60 hertz across it according to the frequency and the capacitance of the capacitor. So anyways, this gave me some ideas to reproduce this myself. Transformicom basically reproduced the high impedance phenomenon circuit, used these round doorknob capacitors that are usually strontium based AC capacitors with a nice carbon rod spark gap here, and a potted 10,000 volt 60 hertz transformer, usually with a 120 volt primary. So anyways, I'd like to get back to my setup, which I'll show here, and some really interesting things I'm going to show you. But basically, here's the setup, the late setup, I would say, where I essentially have an acrylic cube with its bottom open, and it measures 1 cubic foot in volume. And that was later used to cover and contain all the vapors and ozone and all the flying dust and sand that was inside the effective test area. And you'll see what I mean, why I did this in the first place, because it was actually quite dramatic, and it needed to be done because it was just making a mess, and my electronics were going haywire because of that dust and ozone mixed together. So yeah, let's go to the videos of this, and I'll go back to the pictures later. So in this video, we'll see that I have a wand or some sort of electrode that puts me at a distance from the high voltages for safety, and then we have another electrode from the other side of the transformer, just stationary, just positioned above it. And you see that I've done a little bit of the testing, and I just wanted to roll the cameras because it was quite interesting. So before I start this, the spark gap of a 10,000 volt transformer is usually pretty calm, pretty yellow, but when you have a tank capacitor set up, it's very much different. Very much the capacitors discharge all of their stored energy in an instant, which heats the air up incredibly so, and you get a very white arc instead of a calm yellow arc, like a low temperature flame. So let's go ahead and play this video. So yeah, you can see that it immediately sends all the small grains of dust into the air, and this dust was just ground up lava rock in a mortar and pestle. So there's a mix of different grain sizes in this. Yeah, and just a very whitish blue arc, very powerful. Below it you see some wax that I've set up in there to give it a little bit of terrain. This was initially going to be a dendritic ridge experiment, but the findings here were just too interesting, and I abandoned it for just playing around here with the conventional side of the circuit using the tank capacitor. There are other interesting things that go on with this Tesla hairpin circuit, but that's not the focus of this video. So yeah, white arcs, and you can see that there's actually quite a bit of wind too, and that could be from the heat, or it could just be from the violence of the arc vaporizing the air, which creates a pressure wave. And you see here that there's a little bit of reflectivity now, and that's from the wax being melted. I am pushing the electrode down into the wax for that to happen, but it just sort of drives the point that this arc is very hot. It's hotter than usual arcs because it's got a tank capacitor discharging across it, and that's creating a bit of a crater zone. And the dust is sort of rising up a little bit. I'm sure that it's interacting electromagnetically, gaining some charge and distributing across. You can see some of the dust grains jumping about at the end there, as the one electrode is just discharging to the leaky capacitance of the environment. Alright, and in the second video, I'll just distribute some of that crushed lava rock into the previous experiment. And I'll fast forward here because I really want to showcase, I suppose, the effects of the dust. And I don't know if I mentioned this, but I put a welding goggle in front of the camera just because the light intensity is just so overwhelming. So there we see, I'll go back a little bit. I should probably make this just a little bit larger here. We see just so much smoke, and the smoke dissipates very quickly because of the air pressure. And you see, actually, this is quite interesting, ripples back and forth of the grains of lava rock, and it can only be assumed that this is charged grains that are interacting with the field, and either the electric field or the magnetic field or both you know, pointing vector, are just pulling them in, pushing them out in a AC sinusoidal wave, and you get that sort of shape like this, where they're rocking back and forth. Again, we're melting wax, and I wanted to put wax because it sort of sets the shape in place, kind of what you would expect from even higher temperatures of discharges, where it fuses rock together. And I didn't quite have that amount of heat prepared. These capacitors aren't big enough. The apparatus isn't designed for it. We have a wire, and it's not like it would be with a giant thunderbolt of the gods sort of thing. And this is interesting. I don't know if I mentioned this before, but this smoke alarm that's going off is because I don't have a cover over this, so dust is just blowing into the air, and I assume there's also ozone from the experiment as well running, and that triggers these smoke alarms. And this particular smoke alarm is one of those KIDDE smoke ionization smoke alarms, and it uses a piece of like radioactive material. I have it here. It's an old one. Contains 0.9 microcuries of americium-241, and the way that smoke alarm is supposed to work is it detects a constant current flowing between the plates in an air gap, and under normal circumstances it interacts with a regular typical atmosphere, and a expected current should flow between the plates. But what happens when you have smoke or some other particulate in that air gap is it changes that current, and either disrupts it completely, or I would assume enhances that current. And we have a very dirty, noisy EMF coming from these arcs, in addition to micro or milloscopic dust particles and grains and ozone getting into that spark gap. So it very much interferes with the smoke alarm. It's not that it's hot. It's not that heat is coming up to that smoke alarm, although it is. It's actually very, very hot. You can feel the heat radiantly being emitted from this arc. It's not getting to that smoke alarm, which is, I don't know, 8 feet, 10 feet away. Very annoying. And so in the third video here, I've done a little bit of change. I've put the experiment into the acrylic cube now. And let's just get another picture of that acrylic cube. This is what it looks like here. And so that's going to contain that dust and everything else, I hope, and reduce the amount of noise as well as contamination into my room here. So right away, when it first turns on, there's I would say an inrush current from the coil energizing and charging the capacitors. So you'll see all the dust sort of jump for a brief moment, and they may accumulate a charge here. Right? And so now it's running at 60 hertz. You can see a little bit of corona here as it reaches out to the other electrode at a very usable spark gap here. Not sure how I lighted this. Did I move the electrodes? But you can see that there's been a lot of buildup of that dust, and it's been caked onto the electrodes as a result of all of the pressure waves and charge and wax that's all melded together. Very different sound, eh? And you can see when the experiment starts, there's just a blast of dust from the strong forces of the arc. This is probably somewhere in the range of 80 to hundreds of amps flowing through this tank circuit. Every time you see a line here, that's an artifact from the camera where an arc has been established, and then it extinguishes itself, and then another arc will establish itself and then extinguish. And it's very curious to note that you see color here through the welding goggles. You see a lot of green here, right? These are copper electrodes, so we know that it's vaporizing that copper. It's hot enough to do that. It's not unusual for high voltage discharges to eat away at the electrode material, right? That's why they make it out of special material most of the time, but this is just good old copper, right? And then there's most likely dust in the air too, contributing to it. But these are many discharges in a single frame, right? If we assume that this video is being taken at 30 frames per second, we do have like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 different arcs that are captured, and maybe even more than that, in a single 30 frame per second frame, right? So you can sort of get an idea for how often this is firing if you do the calculations. More waves here from the forces. Now imagine a very powerful discharge just raising a mountainside. It's in a more of a catastrophic view of geological formations, but if we can generate a lot of wind from a tank capacitor here, then there's a good chance that we can do that from a giant thunderbolt as well. Steinbacher was very adamant on that perspective while he was still alive. Wax is melted, just going back and forth. The color. Yeah, this is a very, very powerful discharge. And you can imagine just what the other side of the Tesla hairpin circuit is like. Over here you can see the dust dancing around. It's too bad it was an old camera, DSLR camera, just didn't have the exposure control. But I mean, it's hard to really control the exposure in the first place when you have self-illuminated arcs in a room. I think I turned the lights off though, so that probably had something to do with it. But as you can see, no smoke alarm this time, so it was very much probably the dust that caused it, the dust and the ozone. Oh, you know what? I just remembered. The reason why this isn't firing right now is because in the Tesla hairpin circuit, in order to make it work, you need to have that stout copper bar shorted here at B1. And the way that I turned this circuit on and off is I would just disconnect the stout copper bar here and have it open with no loads attached. And when I have it shorted, the capacitors are effectively in series, and the spark gap gets an extra kick, I would imagine. Yeah, maybe higher peak-to-peak voltages, I'm not really sure. But that was what I observed as a great way to make this very aggressive discharge cease. I'm playing with it. Right. So that is the conventional electricity side of the Tesla hairpin circuit. This was done with an old Allenson ignition transformer. Here's the specs. The secondary is mid-tap. That's interesting. Mid-tap grounded. Okay. The piece of aluminum here is grounded. Safety first, right? And what else to comment on? The circuit turns on and off through a switch that I have far away, so there's a little bit of a distance factor to keep things safe. Yeah, so I was trying to get dendritic ridges from these experiments. I did get a little bit of that here, but not to the scale that I was hoping for. But the experiment just needs to be designed in the proper way. This is the aftermath of that circuit here. It definitely looks like there was a lot of heat from it. I've made videos in the past showing just how much moisture gets evaporated from these activities, but they're not hairpin tank capacitor discharges. Those were more conventional, pulse DC, AC. Yeah, so hopefully that was educational, and if you have any comments about this experiment or have any questions or suggestions, leave them in the comment below. And thanks for sticking around.